Hello everyone. Happy New Year. Welcome to 2021. So today we're going to start on 6.1. Chapter 6 is going to be the last chapter in differential calculus. So it is in this chapter that we're going to talk more about what does gradient vector do. And along with velocity vector, then we'll pretty much have the foundation of how we deal with derivatives. And I know some of you might be thinking, well, then what happened to derivative matrix? Well, as I told you, derivative matrix mainly being used as a way to organize all the different partial derivative, and we will use individual partial derivative in our discussion, as well as using row of the derivative matrix, which would be the gradient vector, or the columns of the derivative matrix, which would be velocity vector. But unlikely that we will talk about what does it mean to have a derivative matrix, but rather just pick and choose part of it that we're going to be using. So today in 6.1, the first thing we're going to talk about would be something called gradient field. It's going to be something hopefully remind you of what you have learned in BC calculus. So and we're going to get started, and then I'll remind you, and hopefully or by listening to me talk, you might have a little deja vu. So let's say suppose we have a function, let's say f that met from Rn to R. So let's try to identify this function. I know it seems almost you haven't done any math in this year yet, so hopefully you still remember some of this stuff. So first of all, this function f is a real valued function of several variables. Is real value because the output is a single variable r, while a several variable function because its domain is Rn. Remember that basically implies that have one dependent variable and then have multiple independent variable. And sometimes you don't realize that when you have only one dependent variable, that means you only have one single formula that uses all the variables. We also know that f represent a n-dimensional and n-dimensional surface in Rn plus 1. And probably the most important things that we need to know is the following. Its derivative is called the gradient function. So not f prime, because f prime would either indicate a single variable function, the derivative like the slope of the tangent from basic calculus, or if it's for a vector value function, f prime would indicate a derivative matrix. So in here, its derivative is called gradient function. Now it is in here with the gradient function that I want to talk about. So if you think about it, the function f met from Rn to R, then its derivative would actually be gradient of f, which met from Rn to Rn. And here's the important part. If this is the way defined, is there some way to actually talk about from gradient point of view to the function f? And there is a terminology that I want to talk to you about. In this scenario right here, we can say that gradient of f is basically the gradient function of the function f. So in here, I'm defining the word gradient function, and the word gradient function, what you want to do is to think derivatives. Okay? Now it's a opposite word. And some of you are probably thinking like, what that is, that's called integral or antiderivative. So is there something that's like anti-gradient? And there is. In this case, we can say f is called the potential function of gradient of f. So the term potential function is basically what you would think as antiderivative. So here, when you use the word potential, think antiderivative. So those are correct terminology. Unfortunately, we're not going to talk too much about potential function until at the very earliest, chapter 7. Okay, but we'll probably talk more about it in chapter 8. Okay, but it is basically what the antiderivative is. Now, that's first thing that I want to introduce you to terminology. But second, of course, also is the following. If I do have a function f, and I have a gradient of f, is there some way to graphically represent the gradient of f? So the graph of gradient of f can be represented using something called vector field. So what is that? That's actually very similar to something that you learned in BC calculus called slope field. A slope field is basically allow you to generate the graph of a function and its derivative. And the problem is that the derivative that you learn in BC calculus are literally just slope of the tangent, and therefore we can draw lines, small line segments that represent the slope. But in here we have gradient, and gradient is a vector. A vector needs to convey more than just the direction, which is what slope designed to do, but also a magnitude, and therefore require us to upgrade our graph to something different. So instead of, so here, think about it, the gradient of f, map from Rn to Rn, what does it do is a gradient of f generate the gradient vector at every single point in Rn. So therefore, in this case, when you look at this gradient function, you can identify that the input basically defines a position vector in space that define where it is. And in last year BC calculus, since the output is a single value, we represent that to be slope. But here is a vector value. So therefore, what we have is a vector, which is now defined to be a direction vector. So how is that different when you kind of graph them? For position vector, we basically use a dot to do it. And for direction vector, we use our typical arrows. And of course, important is to make sure that your arrows have the proper length. Okay? So, when a vector field represents a gradient, then is more uniquely referred to as a gradient field. If a vector field represents the gradient of some function, then it is called a gradient field. And we will learn more about gradient field actually in chapter 7, chapter 8. Okay? Because gradient field has some unique property that we want to explore later on. So I guess the best way probably to is to actually look at one and see how that works. So to generate a gradient field is actually very similar to generating a slope field. What I require you to do is nothing more than really just kind of draw it out and then maybe draw out a graph, not of a lot of points. Most likely will be similar to what you learn in BC calculus. I'll probably do either 9 or 25 points depending on how big I want you to generate a field. And you are not expected to generate something extremely accurate, but accurate enough that get the idea across, because to actually properly generate something like this, a gradient field or a vector field, is usually using a computational device because of the sheer number of calculations involved. But we'll do something very small just to demonstrate the process. And I'll also point out some of the important things that you should know. So suppose we have this function right here. Let's say we have f of xy equal to 1/2 x squared plus y. Okay, now notice that some students often get confused. Here I'm giving you a function f, okay, which is not the gradient. And now the question asks you to generate the gradient field of f. Over this interval, -2 to 2 by -2 to 2. So that means x go from -2 to +2 and y go from -2 to +2. Now be very careful, because in this case I give you a function f, and I did ask you the direction say clearly gradient field, which is a vector. Okay, so therefore please do not just draw the function f as a slope field, because that's not what the question asks you to do. Okay, which some of your classmates did that on their tests. So please don't do that. In some cases, when I ask you to generate gradient field, I can do one of two things. So something make sure you pay attention to right now, because you might get confused when you look at a question. So make sure you pay attention. Okay, when you ask to generate gradient field, you can be given one of two things. You could be given the function f, which means that you have to find the gradient and then draw the gradient field. But you could directly be given the gradient, so you don't have to take the derivative of it and just simply generate a field, okay? If what you're drawing is like a slope field instead of a gradient field, meaning you're not drawing vectors, but you're drawing slope, then you're definitely not doing something right, because I'm not going to ask you to generate a slope field. That's BC calculus question. We're not in BC calculus anymore. We move forward. We don't move backward in time, okay? So keep that in mind. So how are we going to generate this gradient? Well, first thing is to find the gradient. So number one, oops. So let's say we go find, the first thing we go do is let's find a gradient of f first. So if f of xy is equal to 1/2 x squared plus y, then what is gradient of f equal to? Well, gradient of f of xy would actually equal to, remember, is a vector. So it's actually pretty simple. It will be 1/2 times x derivative of x squared, which is 2x, so therefore become just x. And then derivative of y, which is 1. So that's a very easy gradient. Okay? 2. What we're going to do is, how about we generate a table? So how does the table look like? So this is how I usually generate my table. Okay, you do want the top to be x, the vertical one to be y, because I don't understand why students don't do that. The way you set up the table is to help you draw the graph. And the best way to help you set up a table so that you can draw the graph correctly is to orient your table the way the graph would look. So that way make it easier to use the table to generate a graph. So all the horizontal values should be x value, because that's how the graph look like. And all the vertical values should be the y value, because that's how the graph look like. And also, more importantly, I always tell my students to do the following. And yes, you do want to make this table a little bit bigger, because you are going to be fitting a vector inside, which means you're fitting more than just one single numbers. Okay, and also more important is that to put the number for x and y the way it appear on the graph also, meaning negative number on the left, positive on the right. Negative number on the bottom, positive number on the top. So that way, everything oriented the same way as what the graph would be, and you don't have to do any extra processing when you try to draw the graph. Okay, so now let's go for it. So this should be pretty easy. So this is just -2, 1. And as a matter of fact, all of these are -2, 1, because our gradient vector is not changed by y value. And then this are just -1, 1. Oh, maybe I should just... Oh, well, you know what? I'm going to just write it out. All right, there you go. And then these are just 0, 1. 1, 1. 2, 1. So now we have a table. Pretty simple. So now we're going to try to generate a graph. Oops. Now, when you generate a graph, please make sure you understand the following. Because now you have to draw vectors. Vector convey two pieces of information. One is obviously the direction, but two is the magnitude, and that has to be drawn properly to indicate the strength of the vector at that point. One of the most common use for a vector field or gradient field, which we'll learn later on, is to represent it as a force field, like a gravitational field, which each arrow not only indicate what direction the force is being applied to you, but also the strength by the vector itself. So therefore, both of them are important. So unlike in the slope field, where it doesn't matter how long the line segment is, you just need a short line segment, these are now actually important. So what happened is you always want to have room around your slope field, your vector field, so that you can actually draw your vector to the right length. Okay, so keep that in mind. So this is what I'm going to do. I'm going to first start by creating my dot. Okay, I'm going to have 25 of them. And notice that I don't go all the way to the edge, because I want to make sure that I have room. Okay? And when you do a problem like this on your task, I will give you enough room so that you can actually draw your vector field with enough room to extend it outside. So please don't try to put all these dots to fill up the entire picture, because if you do that, you won't have enough room to actually draw your vector correctly. Okay? So what we do, we just simply draw the vector. So I'm going to start with the 0. 0 is easier. So this is vector 0, 1. So meaning we'll just basically go to the next dot if there was a next dot. And this dot will go to the dot on top of it. This one will go here. This one will go here. This one will go here. So now all these vectors point in the correct direction. 0, 1, meaning no left and right, just go straight up. And go up 1 unit. And therefore all of these vectors now show the proper length. Now let's do those two on either side. They actually mirror each other. So this will be go left 1 and up 1. Left 1 and up 1. Notice that if you draw these on your graph paper, it should look nice and neat, and where your vector would point into the correct position. Okay? And now I'm going to draw the last two sets, which are on each side. They both still go up 1, but they go 2 to either right or left. So therefore, this one will probably go something like this. So that's our vector field. Okay, so make sure you remember the following. Make sure your vectors have the right length and the right direction. Okay, very important. Otherwise, you will be marked incorrect. Now, something interesting that I do want to point out, and that's the last I'm going to talk about in slope field before we gradient field before we move on to something else. If you look at it, you can definitely tell that the arrows are actually trying to tell us something. It's trying to tell us to kind of move in a certain way, and then they kind of link together. And you're correct. That also relates to a concept that you learn in BC Calculus. In BC Calculus, after you draw the slope field, you are usually often being asked to draw what we call integral curve. Integral curve are basically when you follow the slope and form a curve, and that is the solution to your slope field. In here, we also have something similar, but not quite the same. In here, what we have is what we refer to as flow line. So flow line is basically the same exact kind of same concept as the integral curve, in the sense that you're basically following the flow, following the arrows to tell you what you're doing. Okay? However, this is extremely important that you definitely need to write down is the following. It's that the flow line does not represent the potential function. Okay, it does represent something, but just not the potential function. We will actually talk more about the flow line in chapter 8. I would say chapter 8.3. 8.4 actually, I think chapter 8.4. And we'll also explore more of what is a flow line in differential equation if you're a junior. Okay, but there are definitely flow line that you can think of that kind of follow. And here, the best way to interpret it is to imagine that you are looking at the water being water floating, like in a river. And if you drop something into the water, it would then start moving, following one of these lines. Okay, so in this case, I can definitely see that there's one main flow line that go right in the middle. And then you can see that all the other flow line, if it's on the right side, meaning first and fourth quadrant, the flow line would move up and out. Up and out. Up and out. And then if it's on the second and third quadrant, it would do kind of the same thing. It will move up and out. But it will out to the left. So these are referred to as flow lines. Okay? But remember, they are not the antiderivative. They are not the potential function. Okay? They're not. The reason why they're not, because in order for them to be a line, they must be a single variable multi-vector value function. But we know that function f is not one of those. Function f is a real value servo variable function. So therefore, it doesn't fit the definition. But it is relating, and it will be something that we explore later on, or next year in differential equation. So the next thing I want to show you is the following. The next concept is called direction of maximum increase. So imagine the following, okay? And once again, I cannot, the concept described here, well, actually, maybe I do define it in general. So let's say given a function f that maps from R and to R, with its gradient function, oops, let's say gradient of f, which map from Rn to Rn. Now imagine the following. Imagine we're given a direction. Given a direction vector u, with the length of vector u equal to 1. We can then define df over d vector u is basically what we call the directional derivative. We learned in chapter 5 of f in the direction u. Now we really didn't, well, I did try to explain to you what it is. So let's recap what does it mean. So what does df over d vector u do? So df over d vector u basically give the slope. In this case, you can also think of the increase or decrease, the change in the function f in the direction u. Okay, so therefore meaning that if you take a step in the direction u, the slope kind of give you how far you have to go up or down, the change. Okay, because of that, what if we want to answer this question? What if we want to answer this question? Let's say you're at, let's say we're trying to answer this question. Let's say at a specific position x sub 0, how to find the direction vector u so that df over d vector u at that x sub 0 value is at its maximum. So that's the question that we try to figure it out. Okay, so essentially what does it basically mean is that if you are, imagine you are going hiking and you're standing in this position and you try to look at all the different directions that you can go, and you're looking for the direction that give you the biggest altitude gain. Okay, meaning the one that climb the most. Which direction would you go? Well, obviously, if you're on the side of the mountain, you can probably visually identify which way it is. But of course, in here, we talk about mathematically. You have a surface, function f, and now you are standing at this point x sub 0. Is there a way to determine the proper direction that would give us the biggest increase, climb up the highest on this surface? And if you think about it, doesn't this kind of sound like a optimization problem? And it is an optimization problem. And they actually have a very simple solution to it. So I'll show you how that's done. So imagine the following. So let's say we're given a function f and a direction vector u. And of course, in here we define vector u to have a length 1, so that we have a directional derivative. Based on what we learned in 5.3, we know that df over d vector u is given by this formula, gradient of f dot vector u. Therefore, at a specific location, x sub 0, df over d vector u at x sub 0 will be equal to the gradient of f of x sub 0 dot product vector u. Now notice the function f is fixed, x sub 0 is fixed. The only things that changing is basically vector u. So this is technically our variable. Okay? Now the question comes down to what different value of u would give me the maximum value here. Now that's kind of hard to do. The reason why it's hard to do because I actually should say variables, because it really depends on vector x, vector u, the dimension in. So we could have multiple coordinates. But I can actually change that based on something that I learned in chapter 1. In here, I can basically go in all different directions. But I also know the following. If I perform a dot product between two things, I can actually rewrite it into this. So from chapter 1, we also learned that I can actually form this value by looking at the length of the two vectors multiplied by cosine theta. So now it becomes much better because now we have a single variable that we can deal with instead of in here several variables that we have to deal with before. Because now this value now basically defined by the difference between these two vectors, the angle between them. And also note, vector u has a length 1. So therefore, meaning that from what I'm looking at right now, the directional derivative is actually entirely dependent on two things. The gradient vector at x sub 0 and cosine of the angle theta. Okay, so this theta basically now represents the angle between gradient of f and vector u. Now, let's try to examine what is the maximum value of this expression. The maximum value of df over d vector u at x sub 0 would be when this expression, gradient of f at x sub 0, cosine theta, is at its maximum. Now, the gradient of f of x sub 0 is a fixed vector, so therefore it has a fixed magnitude. Cosine theta is the things that are actually changing based on what different value of theta is. And because cosine is a well-known function, I know exactly where the maximum happened. The maximum value happened when theta is equal to 0. Because that gives us cosine of 0, which is 1. And that gives us the maximum value. Therefore, it indicates the following. Indicate that in order for us to maximize this directional derivative, I need the angle between gradient of f and vector u to have a 0 angle between them. And now if you think about geometrically, when two vectors have a 0 angle between them, what does that tell me? It tells me that those two vectors are parallel. They go in the same direction. And therefore, arrive in our important conclusion. df over d vector u has a maximum value of the length of the gradient of f. That is called the maximum rate of increase. In the direction of the gradient of f. So this is referred to as the direction of the max rate of increase. Max rates of increase. So the important part about the gradient, which we just discovered, one of the important aspect or application of the gradient is that the gradient actually point in the direction of maximum increase. Okay, because it requires the direction that we move to be has a 0 angle between the gradient for it to yield the maximum value of our directional derivative. Now, one last thing, and that's it for today's video. What if we want to have the least amount of increase, or actually, I probably shouldn't say that, I should say this. This function here have a maximum value of decrease, minimum value of negative gradient of f. This often referred to as the maximum rate of decrease. In the direction of negative gradient of f. And that's usually referred to as the direction of the maximum rate of decrease. So essentially, if you're looking for an application of the gradient either point in the direction of the maximum increase, meaning if you go in the direction where the gradient is telling you, that gives you the biggest gain in your function. It gives you the highest change in the function. But if you go in the opposite of the gradient, then you get the biggest decrease in your function. Alright, unfortunately my time is up, so I'm going to have to talk to you guys on next video or tomorrow during class. Alright, talk to you guys later. Bye bye.